For geometric progression, it's kind of similar, but there's another kind of a different way of doing things. Instead of adding, things are multiplying here, simply. So you start with A again. Let me see the notation in the notes. Yeah, let's say you start with A1 again. Now instead of adding, you multiply. So you got A1 times, it's called R. A1 times R. Then again you multiply with R, so it's A1 times R square. And it continues. So can anyone tell me what will be the nth? A1 times what? The nth one.
R power n
How many?
minus.
1. Minus 1, exactly. N minus 1. Perfect. Because the same thing, right? In addition, it was n minus 1 additions. Here it's n minus 1 multiplications. So similarly, you can understand that Tn will be A1 times R to the power n minus 1, right? And here it's same. You see that it's multiplying R by R. So it's, you can do the same thing, but essentially it's nothing but Tn minus 1 times R. Okay. And again, Tn minus 1 times. Again, this is called product telescopic. T2 into T1 times R, and then you see that everything cancels out. You're only left with Tn is equal to, when you multiply, now you're vertically multiplying. So you see, again, this double counting comes up, this double calculation. This is very important because in mathematics, you will see this everywhere, that we have an expression to find, we have a problem to find. We have to actually, we think we have to find this way, but you do the horizontal calculation or the totally orthogonal calculation to get it. And both turns out, all the equations, RHS is equal to RHS, LHS are found out in this way. There are two different ways of counting. And this is a very, very important problem solving strategy. Keep it in your mind. So when you multiply this all over, you get T1 and you see there n minus 1 such. So it turns out. So again, the same thing. This is a called product telescopic. Okay. So this is the recurrence relation we have found out. Similarly, the analytical form, and we have talked about how to interact with it. All of you got this, guys. I'm going quick through it because you have seen this before. I have done it the same way. I am mostly interested in the students who are not from math, stat, and heavy stat background. Let's see what else we have to learn. Okay. So yeah, another interesting thing, both in previous case and this case, is, if you like cut it anywhere, and if you start with this, it's still an AP. Okay. So what is the relation? If you start with TM in both AP and GP, AP and GP are very similar, and I will show you another thing. If you start with TM in AP, essentially to go to TN, instead of starting with TM, T1, you start with TM. Then what you have to do? In this case, you have to go as many places. So when it was n and 1, it was n minus 1. So in this case, it will be n minus m times d. Because starting from Tn, you have to do n minus 1 steps, jumps of d length. And here also, you have to multiply that r to the power n minus 1 times. So when you connect these two things, it's very easy to remember and very easy to understand. So starting from T1 also, it's an AP, it's an GP. Okay. Again, here also another important thing. We can also do the same way, same calculation here. So if you start with A1R, A2R, A1R square, A1R to the power n minus 1. If you reflect it, A1R to the power n minus 1, A1R to the power n minus 2, A1. And if you again multiply it, if you call it P, if you again multiply it, so you get P square, right? And if you see, there are n terms, but each one is of A1 r to the power n minus 1. If you observe A1 square r to the power n minus 1. And there are n terms, so it's whole to the power n. So you get, if you observe it, am I doing correctly? Yes. Yeah. So you see, come multiply this, you multiply this. So you get P square is equal to this. And if you take a square root of it, so you get the A1 comes out, A1 whole to the power n. That's cool. Okay, now let's think about this. So if you observe, again, it's nothing but n by 2. Let me just see. Yeah. I would rather like it like this. It's square root of A1 times A1 to the power n minus 1 whole to the power n. So it's rather square root of T1, T2, Tn whole to the power n. Now, if you remember, in AP, the sum was half, rather, n times T1 plus Tn by 2. And in Pn, it is square root of T1 times Tn whole to the power n. Okay, I probably went it fast. Did you understand why this comes? This one, did you understand? We are just trying to find out, number one, the recurrence relation, number two, the analytical form, number three, the relationship in the recurrence relation, analytical form, number four, the product of it of T1, T2 dot Tn, or the sum of T1 plus T2 dot Tn, and also this basic properties out there. So I wrote down this one and this one. Did you understand this one? How did it come? It's like same formula, same process using Gauss method, but we do multiplication of that rather than addition of that. Did you understand? Can you tell me? If you didn't understand, I will explain it again. If you do not tell me, you are losing the opportunity to tell me that you didn't understand. You have to work your brain around to understand. Anyone who didn't understand this wants another repeat explanation. So GP is more close towards nature in the sense that things multiply. So that's what you say. It's if it multiplies at the rate of r, that's what GP is. Again, for computer science people out here, it's like the binary tree. How many nodes are there at the end of the binary tree? I don't know who are computer science people out there, but how many nodes are there in the end of binary tree? So it's a GP, because every time 2 increases, Tn is equal to 2Tn minus 1. So at the end of Tn, sorry, An is equal to An minus 1. So An or whatever, An is equal to 2 to the power n. So it's a process of life, how things multiply. So that's why geometric distribution comes up more naturally in nature. And you will see when you learn probability, you will see geometric in nature, geometric progression comes up naturally. In when you will learn geometric distribution, you will see how it also comes. But yeah, this is the physical significance of this. So how things move. In fact, in compounding in finance, you all probably know about compounding. Geometric progression plays a really huge role. And that's why I say that things multiply at a faster rate as you go with time, and that's what is called compounding in real life. In finance or in real life, you must have heard about the idea of compounding. If you, for example, if you practice similar problems, or if you practice something over some time, you will see that it suddenly has a turn in your learning journey, and you cannot predict that point, but you will see that it suddenly changes. And essentially what is happening is that the neurons on your brain are getting connected at this r rate, and you do not know that at what point that r rate, like this 2 to the power r, has crossed the threshold. But initially it goes slow, and then it turns out because of the connectivity of the brain and the neurons in your brain, and that's how it happens. Okay, so you will see that compounding is everywhere in life around you, and it's in geometric progression. If you take log of Pn, we will be teaching about log more, do not worry about that. But if you know about log, it turns out n into half into log of T1 Tn. It will turn out to be n into half times log T1 plus log Tn. And therefore, this turns out to be an AP. So essentially what it means is that if you have this A1R dot dot, or let's write the direct recurrence relation. Tn is equal to A1 or T1 r to the power n minus 1. Right? If you take a log of this, you get. So this is similar to, if you call this Tn dash is equal to T1 dash plus n minus 1 is there, and this is the d. So if you take a log on the geometric series, it turns out to be a arithmetic series. That's important relationship, just to make you understand. And you can see in the relationship how it turns out. This is the T1 dash and T1 dash. So knowing this, so now this inspires two important things, which you're going to mark, is this. So these two are called the arithmetic mean and the geometric mean here. Okay, these two are called the arithmetic mean and the geometric mean here.